So, hello, my name is Zhuravlev from University of Maryland. I'm going to tell you about how proteins switch the unfolding pathways under the mechanical force applied to them in the single molecule experiments. So, from a lot of theoretical considerations in the 90s, it's kind of expectable and obvious that the proteins would fold and unfold in multiple routes. Because you have this folding funnel, basically the unfolded state has high entropy, and every route would lead down to the folded state, and vice versa. But and then it's been observed in a lot of experiments, but mostly with multi-domain proteins or repeat proteins. But it hasn't been that often observed in small globular proteins that are single. And this is kind of surprising, but then if you think about it, so if you have a barrier, then if you have two pathways, like on the picture on the right, and you have two different barriers, say, the delta G barrier, the lower one and the higher one, then the ratio of fluxes through this two routes will be proportional to the expression below. And that means that if the difference between this barrier height is not around kT, you're not going to see the flux through the higher barrier. So that's probably why it's not observed that often, but nonetheless, there have been some ways, experimental ways, that do it. So if you cannot observe something in protein as it is, you can perturb its energy landscape. And basically, the two ways to perturb it that come to mind is to apply a force in a single molecule setup, or just do bulk experiments with denaturing. And these things actually do just linearly affect the free energy landscape, and then if you work out the rates, you will get the expressions below. So this is something that's called Bell's law for the force as a perturbant, or you get the Sherman plot for denaturing perturbant, and that means that if you plot the unfolding rate as a function of your perturbation, it's going to be a linear plot on a similar graph. Okay, so and the experiments that I've been talking about, there have been a few. One of them was by John Clark more than 10 years ago with I-27 domain. So basically, you see this log unfolding rate plus the function of denaturing, and they're not linear as you would expect, but actually do have upward curvature. And also Susan Marcus did single molecule experiments with force, shown on the bottom of the slide, with SAR-SH3 domain. You also observe this upward curvature. So, in most of these works, they correctly argued that this upward curvature cannot be explained by a one-dimensional landscape that has one or more barriers to cross, but there has to be a pathway switch. And we really have shown rigorously that basically one-dimensional landscape is not compatible with upward curvature. So if you look at the landscape on the left, that's what we would call weakly multidimensional. That basically means that one reaction coordinate is enough to fully describe your folding and unfolding, and so there is a minimum for each value of reaction coordinate, and it's the transverse coordinate are equilibrated fast. So, and starting from, if you look for mean first passage time on this landscape, you can work out that it cannot produce an upward curvature in the plot of the unfolding rate. And then if there is upward curvature, then that means that it's strongly multidimensional. That would imply either parallel pathway like in picture B, or something else like in picture C, and these plots below show actual simulations on these two-dimensional landscapes, and we do indeed see the upper curvature corresponding to parallel pathways. Now, let's get back to the proteins, right? So this is the SARC-SH3 domain, which was used in the single molecule setup in Susan Marcus lab, and we repeated this in simulations. So this is a small protein, about 60 residues in length, and the force is applied near the ends, and if you measure the unfolding rate as a function of force, so you see this upward curvature. So on the right, the graph is from experiments from Susan Marcus lab, and we see also the curvature in our simulations on the left, and the inflection point is in the similar position. So on the way how you judge if there is curvature or not, well, I mean, it's obviously on the right, but on the left is left, but you fit it with single exponent or with double exponent. If the latter fits better, then you say there is curvature. Now, but then you look at this double exponential model and you're kind of tempted to say, okay, so this is the two pathways that are exactly like Bell models, but now they're stuck together and switched. And if you only have this graph, probably that's as much as you can do. But since we did the simulations, we can look at actual transition state ensembles and see what happens there at different forces. Right, so we found transition state ensembles from our trajectories through we fold the commuter probability, right? So we take the structure, and if half of trajectories from that structure go to folded state and half to unfolded, that belongs to the transition state ensemble. So we can look at the structure of the transition state ensemble, and indeed, at the lower force, 15 piconewton here on the left, the structures are different from the ones on the right. And structurally, that means that at lower forces, the RT loop, this blue-green loop, builds first of the protein, and then it unfolds. So this is the so this RT loop, right? At lower forces, that dissociates from the protein core, and then the protein unfolds. And at high forces, the N and C terminal beta strands, they dissociate, the RT loop stays in place, and then the protein unfolds. So I'm going to show this movie. Okay, so, and we can actually look at every trajectories and see the fraction of trajectories that went through each of the pathways at each force. And we see indeed that as the force increases, the fraction of trajectories that go through the pathway where RT loop dissociates from the core first decreases. Right, but then remember the fitting of the log rate curve, and then if those sum of two exponents were indeed just two pathways that were there, that model also tells you what the flux would be as a function of force. And then that's the black curve down here. And you see that's not the case. So the real case is more complicated than just taking this basically two Bell laws and stack them together. And also when we look at fitting parameters, right? So this is the double exponential model. From simulations, we got some values if we fit the graph, and those are similar to the values in the experiment, but we can also look at the transition state ensemble and see the actual end-to-end distance in those transition state ensembles, and see that those values are different. And then we can have a similar case for the rays, actually. Okay, and the measurement is kind of the same case because mathematically it's also linear perturbation. So, and here this M, which is usually associated with solid accessible surface area, plays the role of X in the previous fitting. And this one has different difficulties in interpretation because for low the natural pathway and for high natural pathway, the difference difference in M is several fold, and it's sort of hard to imagine why would you have a solid surface area so different of the same protein. But if these are just fitting constants, they can be anything. So that kind of explains it. So to corroborate further our picture of switching the pathways, we engineered a mutant and disabling the R2 to peel off with the sulfide bridge. And we run several trajectories you can see unfolding. So the upper bound for the unfolding rate is tenfold smaller than for the wild type. So this is something that can be checked experimentally. And there was another mutation that was actually done in experiments with the Marcus lab, is V61A. So this 61 residue is in the C-terminal beta strand. So it supposedly weakens the interactions between those beta strands and makes the higher force pathway easier. And that indeed what they observed in experiments, and we also observed in simulations on the lab. So the switch in pathways moves to lower forces, and also you see that the fraction of trajectories that go through our loop pathway is always lower in the mutant than in the wild type. So this is pretty remarkable because for this mutation we didn't change the force field that much. It was only a mutation. So to conclude, we have shown that if you have upward curvature in this log rate plot as a function of perturbation that is linearly coupled to your free energy, that implies that your landscape cannot be one-dimensional, it's strongly multidimensional, and in this case, parallel pathways. And mechanical force reaches the pathways in SH3 domain, which we observed in experiment and simulations. And if you want to fully explain the data that you obtain in experiments, you actually have to perform some computations and theoretical considerations. Otherwise, you are just left with fitting of some model, and we don't know whether the fitting parameters have any meaning. And we made a few predictions or experimental suggestions, so you can do a sulfide bridge mutation with R2 loop that I have shown in the SH3 domain, and then you should observe the decrease in rate, or put Fred labels there, so then you see the switching pathways. And since I27 domain shows multiple pathways in the measurement setup, we should also show them in force setup. So I want to thank people who are authors in this one. Mike is now a professor in Case Western, Sean is a postdoc at Harvard. They were members of the Thermalike group, and Susan Marcus is our collaborator in Berkeley. And I thank the whole Thermalike group for support and NSF and NHU Fund.
Time for one or two questions.
I guess I just had a technical question, which is that, I mean, your formulas of fitting had the force only in the free energy, whereas I thought people like Olga Dudko and other people have argued that in order to fit these curves, you also need to include the force dependence of the prefactors and have a more complicated version of Bell's formula, essentially. Have you looked at that at all for these more complicated?
I haven't for this data, yeah. You could do that, I suppose, but I don't think it changes the picture.
Hey, I might have missed this, but could you say a little more about sort of the nature of your simulations? Is this all LMMD or?
No, these are coarse-grained simulations that we use the force field that we developed in the group. They are structure-based, but not only structure-based because they take into account immunized identity.
So it's like one beat, one residue?
It's 2 beats per residue.
Thanks.
Backward section.
It seems like the system and work may be relatable to the fluctuation theorems, where you can, measure the work of unfolding and then apply the, Crookes theorem, Jarzynski inequalities, and that sort of approach. Is that feasible, and have you considered that?
I did not. I think you still need to run a lot of trajectories, right? So
But you can actually experimentally measure the force of unfolding in systems where you
Oh, in
can the
experiments.
ends. So
Yeah, well, we don't do experiments, right? So we do simulations.
well, you talked about this can be verified
Yeah,
experimentally.
they could, but they don't do this kind of. But I think you need a lot of trajectories for that theorem to work. I think they typically have about 30 per point, or maybe 100 per point, and to do Crookes theorem, it's
Right.
like thousands maybe.
Yeah, to get the average work.
Yeah.
Okay, thanks.
Right, with that, let's thank Pavel again, and we move to the next topic.